Chapter 10, Gases. This will be our first segment as we talk about the molecular nature of matter and the properties of gases. What you'll be able to do is describe the properties of gases at the everyday and molecular levels. We'll explain the measurement of pressure using the barometer and a manometer. We'll use the gas laws of Dalton, Charles, Gay-Lussac, and the combined gas law. And we'll perform stoichiometric calculations using the gas laws and Avogadro's principles. We'll apply the ideal gas law and explore how it incorporates the other gas laws. We'll use Dalton's law of partial pressures, and of course we'll study the collection of gas over water so we can see exactly how it will work in chemistry. We'll use the kinetic theory of gases to explain gas laws at a molecular level, and we'll explain the physical significance of the terms in the van der Waals equation of state. So, a few additions here. If you've already done gas laws in Chem 110, then you're probably familiar with Boyle's law, Charles' law, Gay-Lussac's law, PIV-NERT, PV equals nRT. So you're going to see a recap of those things, and then you'll also see our new one will be the van der Waals equation, so how we treat a real gas. So properties of common gases. There's offer little physical resistance. In other words, we can move gases around pretty easily. We can compress them. We can expand them, right? Think about your car tires. We can use them to exert pressure, so we can blow up balloons. And of course, the pressure would depend on the amount of confined gas. If we fill a container completely, so like a glass of water can be half full, but gas will expand to fill its entire container. So you can't fill the container half full, right? So once we put a gas in a container, it will occupy the entire volume of the container. We can mix them freely. So air is a mixture, perfumes are mixtures. Pressure rises and falls with temperature. So we're going to look at that dependency as well. Observations would suggest that there's a lot of space between the molecules. Molecules are going to be moving at high speeds. The molecules collide with walls of the container, right? And hopefully that should make sense to most of us here. That's where we get our pressure from. The pressure is a force over an area. So if we think about the area being the walls of the container, and then of course the collision of the molecules into the container, that would be your force. You have a force over an area, that's what gives us our pressure. Molecules will move faster at higher temperatures. Hopefully that makes sense too. After studying energy, we know that heat is a form of energy. So if I have a little molecule and I give it energy, it's going to move faster, right? All right, so based on the previous descriptions, which analogy is likely the best one for visualizing the behavior of gases at the molecular level? In other words, gases are like a swamp with a lot of animals crawling around, concrete being poured, ping pong balls bouncing around in a plexiglass container, or a bowl of jiggly jello. And hopefully you think it's more like a ping pong ball bouncing around in a plexiglass container, because that's exactly a great analogy. All right, some properties. Despite wide differences in chemical properties, right? All gases, so regardless of what the gas is, all gases more or less obey the same set of physical properties. They're interrelated, which is pressure, volume, and temperature, and then of course the amount that's there. Okay, so there's the amount of gas, the pressure that's on the container, the volume of the container, and the temperature at which the container is set at. Those four physical properties are used to describe all gases, regardless of reactivity, type of gas, size of molecule, yada, 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 whatever it may be. Doesn't matter, whatever pieces are there, those are the four things we use to describe any given gas. So let's take a look. Pressure, as I pointed out, is force over an area. So pressure is force per unit area. Earth exerts gravitational force on everything with mass that's near it. That's weight. Okay, that's not mass, that's weight. Whenever we're measuring the Earth's force, that is going to be a weight. What we call weight is gravitational force acting on the object. So force versus pressure. Consider a woman wearing flat shoes versus high heels. The weight of the woman we'll say is 120 pounds. The pressure on the floor, though, is going to differ greatly. For instance, if we look at the flat shoe, then you have a 10-inch area on the bottom of her shoe. That's going to exert a pressure of 4 psi. But if she's in high heels, then only 0.4 inches of her foot is actually touching the floor. That means you're going to have 750 psi. So if you want to put on high heels and kick somebody, then they're going to feel that force a lot differently than if you just kick them with the flat of your foot. So why flight attendants do not wear high heels? All right, so flight attendants have to wear flats, and that's one of the reasons why. Ways to measure pressure. So atmospheric pressure is the resulting force per unit area when Earth's gravity acts on molecules in air. Pressure due to air molecules colliding with the object. All right, so when we're looking at atmospheric pressure, we're looking at the resulting force per unit area. It's Earth's gravity that's acting on the molecules in the air, and pressure due to air molecules colliding with the object. So one of the little tricks I've learned to use when I was in college that makes perfect sense as I think about it, even in today's worlds. When I think about pressure and what's going on, you can think about it as a column of material above you. So here in Delaware, we're at 1 atmosphere pressure, give or take, and we're at sea level. So if you think about the column above my shoulders going all the way up into the sky, I'm holding all of those gas molecules up. Right? So Earth is trying to pull them down, I'm holding them all up. If I go up a mountain, I'm cutting into that column of air, means pressure is going to go down. If I walk into the ocean and I get a foot of water above me, now I'm holding a foot of water and all of that column of air that I was originally holding. All right, so just something to keep in mind. That's what you're holding on to when you're looking at pressure. Now, another way to measure pressure is the barometer. This is the instrument we're going to use to measure atmospheric pressure. So, quick picture, what we have is a little dish with mercury in it and then a glass tube that's a vacuum, so it's sealed at the top. There's some air in here, and then there's going to be some mercury in here. Depending on the pressure on the outside, it's either going to push the mercury into the tube or pull the mercury out of the tube. Right? This is the simplest barometer. So the tube that is 80 centimeters in length, sealed at one end, filled with mercury, and a dish filled with mercury. Okay, this is called the Torricelli barometer, and it's good at measuring air pressure. So as we push down on the mercury, that should force mercury up the tube, and then we can measure how many literal millimeters of mercury are in the tube. Okay, weight on the mercury in the tube pushes down on the mercury in the dish. When the two forces balance, the mercury level will stabilize. At that point, we could read the atmospheric pressure. So at sea level, it's said to be 760 millimeters of mercury, and that's because it's 760 millimeters in distance in this tube. If the air pressure is high, that's going to push down on the mercury in the dish. That's going to increase the level that's in the tube. If the air pressure is low, the pressure on the mercury in the dish is less than the pressure from the column, that will decrease the level in the tube, which means the height of the mercury in the tube is the atmospheric pressure. All right, standard atmospheric pressure. The typical range of pressure for most places where people live is going to be 730 to 760 millimeters of mercury. So sea level. The top of Mount Everest, the air pressure drops to a whopping 250 millimeters of mercury. Standard pressure in atmospheres then, so the average pressure at sea level, the pressure needed to support a column of mercury 760 millimeters high measures at 0 degrees C. Okay, so now in ATMs, this is going to be approximately 1 ATM. So your actual conversion is going to be 760 millimeters of mercury is going to be equal to 1 atmosphere. And on the next slide, I'm going to give you a bunch of these. So your SI unit for pressure is actually the Pascal, but that's very small. So we like to use the atmosphere. So the atmosphere is 101,325 pascals or 101 kilopascals. Other units of pressure, an atmosphere is too big for most lab work, so we'll use bar. 1.013 bar is equal to 1 atmosphere, right? So 1,013 millibars. 760 millimeters of mercury is equal to 1 atmosphere. We'll also see torr, 760 torr is equal to 1 atmosphere. And again, at sea level, 1 torr is equal to 1 millimeter of mercury. Okay, now for a manometer, we're going to use to measure pressure inside closed reaction vessels. Pressure changes caused by gases produced or used up during a chemical reaction. So there's an open end, which is a U-tube partially filled with liquid, usually mercury, and then one arm is open to the atmosphere. One arm will be exposed to trapped gas in the vessel. So in other words, they'll look sort of like that. Okay, so now we're going to do our reaction here. We're going to produce the gas. The gas is going to exert a pressure, and that's going to push the mercury through the tube. Or maybe we consume a gas and we pull the mercury back. Okay, so P of the gas will equal P of the atmosphere. So P gas greater than P atmosphere, the gas pushes mercury up the tube. In other words, we're producing gas. P gas less than P atmosphere, the atmosphere will push down the mercury tube, and so then we'll see the mercury go back towards the vessel. So let's see, a student collected a gas and an apparatus connected to an open-end manometer. The mercury in the column open to the air was 120 millimeters higher, and the atmospheric pressure was measured to be 752 torr. What was the pressure of the gas in the apparatus? All right, so this is a case of P gas being greater than P atmosphere. So P gas would equal P atmosphere plus the P of the mercury itself. So 752 torr plus the 120 torr gives us a total of 872 torr. In another experiment, it was found that the mercury level in the arm of the manometer attached to the container of gas was 200 millimeters higher than in the arm open to the air. What was the pressure of the gas? So this time P gas will be less than P atmosphere. So it's going to be 752 torr minus the 200, or 552 torr. So the arm furthest from the vessel, the gas is sealed. So this is a closed end. So before it was open, we were dependent upon the atmospheric pressure. In the closed end, the tube will be filled with mercury, and then the open system's a flask, and some mercury will drain out of the sealed arm. Okay, so now, since it's sealed, we're going to have the mercury all the way to the end, and we're either going to measure the mercury coming back or the whole thing moving, right? So if a vacuum exists above the mercury in the sealed arm, so down here the pressure would be equal to 0, and now we can see as mercury moves, we can measure the differences just like before. Level of mercury in the arm will fall as not enough pressure in the flask to hold up the mercury. So here P atmosphere will equal 0, P gas will equal P mercury, so it's directly read as pressure. In other words, gas pressure is measured using a closed-end mercury manometer. The height of the fluid in the manometer is 23.7 inches of mercury. What is the pressure in ATM? All right, so basically we're going to take 23.7 inches of mercury and convert it to ATM. So we know that 1 atmosphere is going to be equal to 760 millimeters of mercury. We know that there are 1,000 millimeters in a meter, which is equal to 100 centimeters. And we know that 2.54 centimeters is equal to an inch. All right, so there are some general conversions for you. And hopefully you came to 0.792. And again, so you're going to take inches of mercury, 23.7, convert that to centimeters. Here we'll see the inches cancel out. Then we'll convert the centimeters to millimeters. Centimeters will cancel out. Now that we're in millimeters of mercury, we can convert that to atmospheres, and that gives us 0.792. All right. It was found that the mercury level in the arm of the open-ended manometer attached to the container of gas was 150 millimeters higher than in the arm open to the air. The external pressure was 780 millimeters of mercury. What is the pressure of the gas inside the manometer? Hopefully you came up with 630. And the way you did that was you said the P of the gas would be equal to the P of the atmosphere minus the P of the gas. So pressure of the atmosphere minus the pressure of the gas, right? So that means you're going to take 780 minus the 150. All right, so comparison of mercury and water. The pressure of 1 millimeter column of mercury and 13.6 millimeters column of water are the same. So mercury is 13.6 times more dense than water. Both columns have the same weight and diameter, so they exert the same pressure. Okay, so it's only the water and the mercury that are being compared. Using liquids other than mercury in manometers and banometers. So as you know, mercury is considered a pretty poisonous substance these days, and so we tried to not use mercury for anything. So try to develop other systems that can still measure pressure. A simple relationship exists between the two systems. For example, if we use water, which has a density of 1, instead of mercury, which has a density of 13.6 in the tube, then in general, the height of B times the density of B would equal the height of A times the density of A. For converting from millimeters of mercury to millimeters of water, then, the height of the water would equal the height of mercury times the density of mercury divided by the density of water. Use this relationship to convert pressure change in millimeters of water to pressure change in millimeters of mercury. Converting millimeters of acetone to millimeters of mercury. So we can do this with any substance as long as we know the densities. Acetone has a density of 0.791 grams per milliliter. Acetone is used in an open-ended manometer to measure a gas pressure slightly greater than atmospheric pressure, which is 756 millimeters of mercury at the time of the measurement. The liquid level is 20.4 millimeters higher in the open arm than in the arm nearest the gas sample. What is the gas pressure in torr? Now remember, torr is equal to millimeters of mercury. So you can pause here, try it, and then see how you do. So the first thing we want to do is convert the millimeters of acetone to millimeters of mercury. The height of the mercury would be equal to 20.4 millimeters of acetone times the density of the acetone divided by the density of the mercury. So that means it's going to be 1.19 millimeters of mercury. Next, we can add the pressure of the mercury to the pressure of the atmosphere to get the pressure total. So we have 756 torr plus, remember, millimeters of mercury is equal to torr, so that could be 1.19 torr. Adding those together, we get 757.2 torr. All right, this is probably a great place to stop this segment. Next, we're going to start to get into the gas laws themselves. And so we're going to stop here and we'll start segment 2 looking at Boyle's law, talking about how pressure and volume are going to be related.